Atoms have been the subject of discussions ever since early Greece. Democritus was the first to state that the issue comprised of little, undetectable pieces. He referred to them as atomos because he believed they had been indivisible. Hello everyone, welcome to Z, and please don't forget to subscribe. Due to this, we now refer to them as atoms. Naturally, Aristotle believed it to be a terrible idea. Still, I do. How come I created you? Anyway, the argument raged for more than 2,000 years. Finally, the turn of the 20th century was drawing near. And we moved forward. In 1897, Thomson made the discovery of the electron. Made a straightforward atom in 1904. Drifting negative electrons in a positive mist. A superior one was put out in 1911 by Rutherford. He wouldn't find an atomic nucleus, though, until 1919, the proton. Sadly, that nucleus was incapable of being only consists of protons. That would seem improbable. The periodic table's masses. It wasn't until 1932 that the finding was made. To explain it, consider the neutron. It's quite difficult to find neutral particles. Okay, what do we currently know? Outside and surrounding the object are negative electrons. A constructive core. Protons and neutrons make up that nucleus. However, by the time humans were even aware of neutrons, knowing that electrons don't orbit like this, this image is incorrect. So how does it actually appear? Well, this is how it appears, but most likely not what you anticipated. Isn't there something like a visual model? Similar to this, but more precise? Alright, I'll try it, but be ready to experience mind-blowing. In the 1920s, things got pretty strange, so let's try to be as specific as you can with this. As a result of light being produced, everyone can see me by your monitors. In an earlier video, we witnessed the person. Atoms can also produce light. An emission spectrum is what it is. Can identify the type of atom it is? Regardless of the atom's model that is created, I must elucidate that. Let's start with the most straightforward issue. Why do atoms produce light? Levels of energy. Consider a closed glass of hydrogen gas. Tube. If we apply a lot of electricity to it, some of the electrical energy will be absorbed by the electrons. Energy. When those exact electrons recombine, the emitted energy is light. Minor issue, though. If the electron has the ability to jump to any energy, it might produce any hue of light, but we already know only these 4 hues are released by it: 1 red, 2 violets, 1 blue-green, and 1. The electron is the only logical conclusion. Cannot obtain the energy it desires. Only a relatively limited set of energies known as energetic levels and transitions there between levels produce or absorb particular hues. With light, these levels are numbered 1, 2, 3, 4, 5, and so forth. The route to infinity. Nowhere is the electron permitted to exist between the two. Not even for the split second it jumps. It must vanish from one and resurface on another. The opposite, I know, it's absurd, right? But let's get back to hydrogen. The visible spectrum of hydrogen has 4 leaps. 3 to 2, 4 to 2, 5 to 2, and 6 to 2, respectively. Any other jump releases an invisible light. But why, exactly? That is the query that directs us into insanity. When a measurement has a limited range of values, it's quantized, as we say, and the light emitted or taken in during a transition between those values are referred to as quanta. That is correct. We're discussing quantum mechanics here. We are aware that when objects orbit due to gravity, they are free to use any energy they like. The mechanism is classical mechanics on how that functions. These laws don't seem to apply to electrons. However, therefore, we required of quantum mechanics, quantum particle mechanism. Returning to the chronology, a French physicist by the name of Louis de Broglie made a suggestion. What if electrons could behave like waves? Only at a specific energy level can the electron exist. Levels, since a whole number is required. Existence of wavelengths. They aren't even orbits in reality. This required some unconventional thinking, although it did resolve a few issues. 1. Why are electrons limited to a particular energy? Levels? A wavelength would be like being chopped in half. Up an electron. Ridiculous. A simple leap from one level to another. Whole electron wavelength gains or losses. 2. Charges in motion must produce light. As to why electron orbits don't collapse, motion that accelerates is an orbit. Electrons need to be constantly losing energy into the nucleus and come to light. However, they don't. Why not? They aren't actually in an orbit. They are merely waves. However, if a wave, such as light, can come in little tiny packets and particle-like packets, like how waves can resemble electrons, why stop with electrons? A scientist from Austria named Erwin Schrödinger pursued that idea vigorously. If every particle is a wave as well, then we will require a wave equation to foretell their behavior. Maxwell's equations provided the following results. That sort of thing is this for the light. All particles are what we want. What may be inferred from a particle's total energy, we contact the Hamiltonian and receive information that resembles this and is intended to let the wave function aid us with this. A formula that captures all the characteristics of waves a particulate. But there's still a tiny issue. Even if we consider the electron as a wave, is still accelerating when it is in space. Motion. It should still be producing light continually and tumbling toward the core. The electron must not exist as a solution. Waving. Be patient. You just said it was waving, didn't you? Yes and no, I suppose. Okay, I believe it's time for another summary. Protons and neutrons make up the nucleus. Furthermore, surrounded by an electron cloud. All those particles' behavior is controlled by through wave functions. However, if the particles aren't, what exactly are you doing when you wave? A German physicist by the name of Max Born into the conversation and made a suggestion. It might very well be a wave of likelihood. I am aware that it's crazy, but it resolves every issue. I believe Richard Feynman best articulated it when he said, the electron's wave function in an atom does not describe an electron that has been smeared with a uniform density of charges. Either the electron is here, there, or regardless of where it is elsewhere. A charge of points. Huh? Okay, so here's how it functions. A particle's attributes are waves even though the particle itself is not one. The location, the activity, and the amount of energy it possesses, all of these objects have a wave-like shape. However, they are merely probabilistic waves. Suppose an electron is in the following position, this. It isn't spread out over the entire area. Simply put, it lacks a firm position. It's most likely here, but it's either likely to be here or here. None of these sites won't be. However, it might be almost anywhere. What occurs then if I attempt to measure where it is? There will only be one location. Simply put, you can't anticipate where that will be. Measuring anything modifies what is measured. Image of a wave. The wave shifts from this to this, but even then, the specifics are unclear. There is still some space for error. The uncertainty principle is this. It's about. However, the measurement does not invalidate the wave. It merely reduces it to a more basic shape. Fortunately, some calculations can be done jointly. The energy and angular momentum size and at least a portion of it can all be measured jointly, allowing those to be determined simultaneously. However, there is still a slight spread. There is some leeway, which is what provides their thickness in emission lines. However, these metrics' clarity provides a wealth of knowledge on electrons. Using atoms, information is what we utilize to group them into orbitals and shells. Okay, last word. Protons and neutrons make up the nucleus. Furthermore, surrounded by an electron cloud. All those particles' behavior is controlled through wave functions. However, since those are probabilistic waves, everything is at least somewhat ambiguous. We are unsure of everything's exact nature. No idea what it is doing or where it is, but we can make a few excellent educated guesses, and that's sufficient to foretell the full periodic chart. Have any questions now? Ask in the comments, please. I appreciate you watching and spreading this video. If you wish to, don't forget to subscribe. Adhere to us. Until then, keep in mind that it's okay to get a little bonkers. We experimented with a novel kind of video, and everyone seems to enjoy it.